and I'll be the first point of contact if you have any questions regarding source after the presentation. I wanted to bring your attention to a couple of things first. One is that this presentation is an advanced water management webinar, and it's being broadcast in the lead up to a 2-day course that will be running in Brisbane on the 17th and 18th of November. The other thing that I would like to bring your attention to is that some of the features that you'll be seeing today are only available in the full version of Source. There's a public free version of Source available for the majority of your needs, but if you'd like to see the difference, it's available in our online documentation. I'm just showing that to you now. So our online documentation includes the user guide, the scientific reference guide, and the differences between public and full versions of Source. People attending the course will have the opportunity to play with the full version of Source during those 2 days. I'm going to hand you over now to two of our hydrologists, Jeff Adams and Karina Redpath, and there'll also be other hydrologists and developers on board to answer your questions as they arise. So one moment, please.
Good morning, everyone. I'm Jeffrey Adams, and I'll be doing most of the presentation this morning. I also have Karina Redpath and Jeff Davis, our software development leader here, who will also be assisting with the presentation. I have over 30 years experience in the water industry, largely in water resource management, modelling and running systems.
I'm Karina Redpath. I'm a senior hydrologist. I have about 12 years experience in water modelling and been with eWater here for a couple of years now.
I'm Jeff Davis. I'm the software development leader, and I've been involved in one way or another with Source and the software for about 10 years.
And first picture, I couldn't get the page to go down. So this will largely be PowerPoint, but we will step out a few times and look at Source itself. So you can see on the screen there the aspects of Source we'll be looking at, so I won't read through that list. I'll be putting that up time. Just as a bit of background, the version of Source we're using for this is the latest beta. That's 3.8.16. The presentation is aimed at experienced users. Some of what we cover, most of you will already know, but I hope that everyone in the audience learns at least something new about Source. So, phases. There are over 20 phases in Source, but the three main ones are shown here on the screen: the constraint phase, the water phase, and the flow phase. So the constraint phase runs from top down, as shown on the diagram, and so that works out and tracks the minimum and maximum constraints as you move down the system. The order phase then moves from the bottom up, and it collates the orders, some up, moving upstream, but subject to the constraints which have already been determined. And then in the flow phase, the system what really can happen. So, function time of computation. A lot of the time this doesn't matter, but when it does matter, it's very important. So I'll just give a very brief demonstration of the function time of evaluation, and I'm going to step out to one of the source models, which was just created purely to illustrate this. So you can see on the right, we've got the function manager screen, and you can see that I've defined some model variables. And I'll just go into the editor and explain a little bit about these. So these are all to do with the inflow, and I've made the minimum flow a function of the inflow. So the model variable inflow flow is set to the value of the inflow, and it is defined at the ordering phase. Now, you may recall what I spoke about the order of the phases are evaluated: constraints, ordering, and flow. So if something's evaluated in the ordering phase, it's available in the ordering phase and the flow phase. If it's evaluated in the flow phase, then it's not available in the ordering phase. issues is that many things evaluated at the start of the time step only have available the value at the end of the previous time step. Now, this particular model variable flow here is often available at the start of the time step because that's a played variable, which in other words, it's from the input data. Often, however, the flow values are not available at the start of the time step. So we've got the inflow flow model variable. The downstream flow model variable here is again evaluated at the ordering phase, but this flow is only available after the flow phase is evaluated. So this particular value looks like this one, but it's delayed by a time step. And then the end of the time step is evaluated at the end of the time step, and so it'll have the value after the flow phase. So then if we look at the the functions, we've got the minimum flow requirement is made 10% of the value of the inflow, and it's evaluated at the ordering phase, so it's evaluated at the time that the orders are determined. It's also available in the flow phase, therefore. We've got the value of the inflow is determined by a function, now.day, so that's simply the day number of the month, within the month. We've got the model flow, which is 10% of the downstream flow, and we've got the model end of time step, which is 10% of the end of time step value. So then we'll just have a look at some graphs of the results. And the modelled versus compared with the end of time step. Just look at the table to make that easier. And you can see that the modelled flow is delayed by one time step. As I explained when we were looking at the model variables, the end of time step is reported as not delayed, but that is only available at the end of the time step. Pardon me. So if you wanted to use this value within the time step, you'd actually be using the previous day's value. And if I look at the inflow versus the requirement, this has been configured carefully and correctly, so the value is actually, the minimum flow requirement is actually 10% of today's value. Whereas had I made it a function of the downstream flow of the inflow, it would have been picking up yesterday's value. So that's just an example of where you need to be careful with functions. Now I'll just duck back into here for a minute and just explain one more thing in passing. If we look at the time of evaluation, you can see that there are a number related to resource assessment. So obviously the resource assessment entry and triggers are related to resource assessment. Post-flow phase is also related to resource assessment. So a lot of these time of evaluations are particular to resource assessment. And again, this one here is also for resource assessment. That's post-function evaluation. Just see if I can find my mouse. So now moving on to ordering systems. And within the ordering systems, I'll explain a little bit about split configuration, Confluence configuration, storage routing configuration, and storage configuration, where they're important for the ordering system to work properly. So within Source, we have two ordering systems. In other words, two ways of evaluating the flow phase, the order phase rather. We've got the rules-based ordering system and a network LP ordering system. This presentation will focus on rules-based. We won't go into the network LP. You get to choose which ordering system you wish to use up here where the red arrow is. You click on that and then you get the choice here whether you use the rules-based ordering system or network LP. All of the configuration options further down are related to network LP, so we won't go into those today. So the things which need to be configured, or the very important things which need to be configured for the ordering systems to work, are circled in red and green. And also the inflows and storage is also the configuration as well. So, as I explained earlier, we'll be looking at the confluences and splitters. So, looking at the splitter configuration. So, the splitter configuration is important because the splitter actually can be configured to order water, which I'll explain shortly. The splitter, of course, also passes orders upstream, but it can also initiate an order in its own right. So I'll go back to the control splitter here. In this particular case, if you can read the way the splitter is configured, you can see that for a given upstream flow, the splitter will pass any amount required down the effluent. In other words, it can pass from no water down the effluent to the maximum upstream flow down the effluent. And so that situation can arise where you might have orders downstream of the effluent, and then the splitter will give will try and give the orderer, whether it's a demand or a minimum flow node, for example, or an environmental flow node, as much water as it wishes. And the rest goes down the mainstream of the river if there's more coming in. In an uncontrolled configuration, as you can see here, the minimum and the maximum down the effluent is tightly constrained. So it's a tight function of the upstream flow. So that could reflect a natural offtake, for example, where there's no artificial control and the amount going out the effluent depends on the water level in the upstream reach. You have to be careful with this sort of configuration though. So consider the configuration I've shown here. We've got an upstream flow of 1,000 megalitres, and that results in a minimum effluent of 1 and a maximum upstream of 1. And that's fine if that's what you wish to happen. Where the danger comes in is if you have a demand or a minimum flow, say, as shown in the diagram over here. If this is configured to require 1, then it requires a flow upstream of 1,000 to get its 1. And so this forces a flow of 1,000 megalitres per day to go upstream. And as you see the results on the graph here, you've got 1 going to the minimum flow node, and then downstream of the gauge you've got 999 what you intended. So you need to be a little bit careful setting up uncontrolled splitters to guard against that. The other useful feature is the regulator opening percentage. So in this situation, the splitter causes the effluent to take 20% of the upstream flow. So I've set up an example here. In this particular case, the downstream flow, so that the upstream flow is 1.25. It's configured to send 20% down the effluent, and so 0.25 goes down the effluent, 1 goes down the main branch of the river. And this particular functionality can be controlled by a function. So next is the confluence configuration. So if you consider the simple example shown here, the confluence needs to determine where to get water from to supply the water user. In other words, the confluence determines whether to send the order up link 1 or link 2. So in this particular situation, both the links are regulated, and so we check both as regulated, and in this particular case I've selected a harmony-based ordering. The other alternative is to select the constraint-based, which is a fairly trivial method of doing it. With constraint-based, the minimum and maximum constraints are complied with, and then the remaining order is determined by the priority. In other words, where possible, it sends the order to priority 1, otherwise to priority 2. With the harmony-based method, we actually share the water between link 1 and link 2. Again, the minimum and maximum constraints are complied with, and then the balance of the order is adjusted according to the harmony rule. So in this case, I've said we've got a function, storage 1 harmony rule, and storage 1 harmony rule looks like this down on the bottom right-hand corner. We've defined up here a volume where storage 1 is the volume in storage 1, storage 2 is the volume in storage 2, and then we just prorata the order according to in this case, according to the balance of the storages. There could be other rules that you have, it could depend on the size of the inflows up each tributary. The volume of storages is not necessarily the only thing that you would harmonise the orders on. And so in this particular case, you can see that the orders have been distributed 1/3 up link 2, 2/3 up link 1. Storage 1 is twice as big as storage 2 in this example, so it's configured that way. So this is an unregulated example where we've got an unregulated inflow 2 coming into the confluence. So the confluence needs to determine how much water to send up to the storage. Now the confluence does a forecast of what the inflow will be for the next time step, and then the balance of the order goes up to the regulated branch. So you can see if the forecast is incorrect, then you'll either send order too much from the storage or not enough. So that's something to consider in doing the forecast. So here you can see default link 1 has been configured as regulated, default link, the other default link is unregulated, and now we no longer get to choose the ordering methodology because it's not a fully regulated confluence. We actually have a forecast option. We've got a range of forecast models available. A fairly common one is to use a recession, and this is where you configure the recession and the trend parameters. A recession is when you recede to 0, but you could recede to some other figure. And you can forecast either from the previous time step or the current time step. In daily models, we generally receive from the previous time step. So you can see in this example, the confluence will forecast that the inflow from the unread trib will be 0.9 of the previous day's time step. Now we also do something similar for inflows. So for example, with these two inflows, we can forecast what the inflow will be in the next time step. Probably not important in this particular model, but in many cases it is. So storage routing. Storage routing, getting the configuration of storage routing right is important in models, because if this was a routing link and there was a demand down here, the system would need to know how long it will take the water to get from the storage to the demand for the orders to be placed correctly. And if the routing link is not configured correctly, it can't actually work out the travel time. So in this particular case, we're using Muscinium type routing. We've got a storage constant of 86,400 and a storage exponent of something other than 1. If the exponent is 1, then this is not so important because it can calculate the travel time. But if the exponent is not 1, then the system can't calculate the travel time unless a regulated flow is defined. So if you've got a system which normally has a regulated flow of 10,000 megalitres per day, you put in the 10,000 megalitres per day, and then the travel time can be calculated, and the system works according to that. If you don't configure this average regulated flow rate, in the newer versions of Source, the model run will stop with an appropriate error. In older versions of Source, it just won't work properly. So storages. The configuration of storages also affects ordering. So consider this case. We've got a downstream storage and an upstream storage. The downstream storage needs to be configured properly for it to take the water it needs from the upstream storage. And there are a few places we do that. So we've got the operating targets. The top two here, minimum operating level and maximum operating level, only apply to weirs. We're not going to go into that today. The maximum unregulated operating target only applies where you have off-allocation water, and we're not going to go into that today. The operating target is the level that storage 2 tries to be at, and so storage 2 will order water from storage 1 so that it tries to be at the operating target. You can see that could be a function. Anything with this ellipsis here is where you define a function, and so you can make this dependent on the time of the year or depending on how much water is in storage 2 or however you like to run it. So in the ordering tab down here, we have other places to configure. First off is the daily evaporation, the forecast evaporation. So when the system is placing orders from storage 2 to storage 1, it tries to consider how much evaporation there will be, and so it orders to cover that as well. We have the option of passing orders through storage. So in this particular case, you might do that for a very small weir, for example. If the water user here orders a certain amount of water, storage 2 doesn't do any particularly clever thinking. It just adds the forecast evaporation volume to the order and sends it upstream. If you don't check that box, then you can forecast the inflow volume, which is what you think or what the model thinks the inflow on the way to storage 2 already is when it's determining how it will meet the target. So if there's a 5-day travel time and storage 2 is trying to get to its target, it needs to know how much water is already on the way to storage 2 from storage 1 to calculate the order for the next day. So it's very important to calculate the forecast inflow volume correctly to get storage 2 to behave the way you wish it to. So moving on to some really useful tools. So I won't demonstrate these, but perhaps just show you where to find them and explain a little bit about it. So with the diff tool, I'll just pick a random model. So diff is under tools. I'll try and make this a bit bigger. Down here, you click that, you get to open 2 different projects, which can be the same if you desire, and then from the projects you've opened, you get to select the scenarios you wish to compare. So you can compare scenarios from different projects or compare scenarios from the same project. It doesn't compare time series data, but just about everything else I think is compared. So if you make a change to a model and you can't work out why you're getting different results, run the diff tool and you might get surprised. I found problems for people where they've inadvertently changed a function or changed some configuration they've forgotten about. All those details will come out. Export summary is another extremely useful tool. It gives you a flat ASCII text file describing the model structure. And it also gives you details of all the parameters and so on, which come up a little bit later in the presentation when we talk about how different ways you can change the parameters, including from the command line. There is a new node available on the node palette called the Scenario Transfer node. Let's have a look at the node palette. And we now have the Scenario Transfer node here. So that's where you've got 2 different scenarios in the same project and you wish them to run as one combined model. So for example, if you wanted an integrated lower Murray model, you could have a Goulburn model, Murrumbidgee model and a Murrumbidgee model on separate scenarios. And using the Scenario Transfer node, you can link all those models together using 4 scenario transfer nodes in total. And they pass the constraints and orders and flows are all dealt with. Those phases are all dealt with by the Scenario Transfer node. It also handles ownership and constituents too, if you're interested in that. And of course, if you want to have those 3 models in the same project, you'll be interested in the import scenario. So you can now import scenarios. So you have a project and you can import a scenario from another project. It's pretty self-explanatory when you get in it. Map view. So this is probably most useful for showing other people. Trying to make this bigger. So if you had a model that looks something like this for our Victorian friends, it's just from Lake Eildon down to McCoy's Bridge, and it's got the house I used to live in when I lived in northern Victoria. What I've done is actually used, given each of those nodes a geographic location, and you can see that in the feature table, which is another really handy thing. So you can see on the feature table that I've given it lat longs. So each of the inflow nodes has lat longs. Each of the storages has lat longs, and each of the gauges has lat longs. You can also use the feature table to do bulk imports of data if you wish. So going back to the data, back to the storage, you see we can configure the volume, surface area, and we can import those from Excel, initial storages and so on. So it's a handy way to get data into the model rather than going to each individual node separately. So since we've given it the geographic coordinates, you can see where the various features are in the geographic view, but you can also see it in the map view. So it automatically grabs a map off the internet, and you can see here we've got a combined hybrid satellite map view. We can also just show the map itself. One disadvantage, of course, of realistic images like this is you don't actually get to see every node, which is why we use a schematic in the first place. So, for example, in Shepparton, I've got a gauge here, located where the gauge on the Goulburn is at Shepparton, but there's also another node hidden by that, which is the confluence between the Broken and the Goulburn rivers. So, if you wanted to see the confluence, you'd have to put it in a incorrect place, or zoom in so far that you can't see anything else. So we've just covered the map view and the feature table. So scenario input sets. This is one of the really exciting things. This scenario input sets allows you to have different scenarios within the same project. In fact, what we used to call scenarios, we're going to rename now to avoid the confusion between these things, which are real scenarios. So, for example, you can have a particular network which is configured for normal conditions. You might like to see what it looks like in the undeveloped stage, for example. And so you can turn the infrastructure off or change the size of something using a scenario. So I'll just give a quick demonstration of that. Imagine this project, which many of you have seen before, and we're interested in the lake release, perhaps changing the requirement. If you go into the feature editor, you see it's 50 megalitres per day. That's the way we did it in the training. That's the original configuration. If we go to the scenario input sets, we can change the value of this. So we go to nodes, lake release requirement equals. Now the system helps you type that in. So if you just type nodes, then you get to choose a selection of a list of all the nodes. So you choose lake release, that's the minimum flow requirement node, and just call that. And then you get to choose which parameter you wish to change, in this case requirement, and then it tells you what the current value is. You see the format, equals 50 it said, so I changed it to equals 20 megalitres per day. You can also import that from a file, and you can select to change to load that at runtime as well. So you can see that gets really excited if you're doing this sort of thing from the command line. You can, within the command line, change the value of parameters in the file. Next time you run it, it loads it at runtime, and so you run different commands. Now, I referred earlier to the export summary text file, and I referred then at that time to the fact that it gives you the parameter values. The parameter values in that export summary text file are presented in exactly this format. Similar format, I've just been corrected. And so anything that's detailed in the export summary file can be changed through the input sets. So you can have not just one, you can have a heap of these that you can change at runtime. So just to run that, you go to configuration, and you're probably all used to seeing the default input set. Every time you create a new scenario, it gets added to this, so you select from the GUI which particular input set you wish to use in that particular run. if you're doing this at run from the command line, you get to choose which input set you're running from the command line as well. So you can see that you can do some really nice things. You can also have child input sets there. So in this particular example, I've said, okay, we'll make the minimum flow requirement 20 megalitres per day. I can then create a child input set under that at a lower level, which in this case I've called pre-development, and I've deactivated the recreational lake upstream. So I've turned that lake off. So I'll just hand over to Jeff Davis, and he will just talk a little bit about using input sets with data files.
Cool, thanks Jeff. So the input sets were initially designed so you can change all or quite a number of time series in your model at once. So if in this example, if we look at scenario input sets, we have three. We have the default without any changes to parameters. We have a dry scenario where we've set the minimum requirement to 20. And I've also got a wet scenario with the minimum requirement set to 70. So if I look at this data source for the Crab Creek inflow, and when I do view data, instead of there being a single time series for me to view, there's three time series. So if we swap it over to cumulative. So when you choose which scenario input set you're running in the configure menu, it will change what time series it's going to be using. So you can set up all your data sources to have multiple files for each input set. So as we have in this example, we have three different files, one for each input set. And so when you run, it will swap out all the time series to be for the right input set. But if we look at fish inflow, for instance, it only has one time series and it is used across all the input sets. So, and you can see that up here where you select which input sets that this file is used, and you can add in more files if you need. Cool.
Thanks, Jeff. So a question has come through about the confusing usage of the term scenario that we've been doing lately, and I apologise for that. So until quite recently, what we used to call scenario in the source world was one of these things here. Within this project, we have essentially three different models. We've got the stage A, stage B, and stage C. And for many years, we've called these scenarios. In this particular example, they almost are scenarios because stage A comes first and stage B extends stage A and stage C extends stage B. But they could also be totally unrelated models. So one could be a rainfall runoff model and one could be a river model, and they can talk to each other. They can talk to each other through the data sources setup, or they can talk to each other through the scenario transfer node. But they can be completely different models. So we're going to stop calling these scenarios, and we'll just use the scenario input sets as what a scenario is, which is a variation of the model. So that's what most people think of a scenario. That is a variation of a model, and we'll call these probably networks just to avoid confusion in the future, but we'll have a little bit of confusion until we move beyond that. I hope that answers that question. I'll say a little bit about resource assessment, and then we'll move on to groundwater interaction. So, excuse me, we have three inbuilt resource assessment systems in Source. We've got annual accounting, which to my way of thinking is the most generic. It can be configured many ways, and it can be configured to do carryover and so on as well. You could configure the annual accounting systems to be almost like continuous accounting, if not continuous accounting. Then there's continuous accounting, which is the New South Wales way of doing things in, say, the NAMWI, and continuous sharing, which is a Queensland specific resource assessment system. We have off-allocation or supplementary flow sharing. We've got special nodes for that. And we've also got different ways of managing unregulated flow. So there are various limits on how much water can be taken. Some of the time you may even prefer to set up an annual accounting system to manage your unregulated flow take. So sitting under resource assessment in a way becomes restrictions. So we've got inbuilt urban demand restrictions. So we have ways of setting up your level 1, 2, 3, 4, 5 type urban restrictions, and you can also restrict demand according to those restriction levels. So that's typically applied in a top-down method, that is, people tend to take as much water as they want, or an urban water authority will take as much water as it wants, unless there is a shortfall of water. In other words, you've implemented restrictions, in which case restrictions are applied and you start reducing demand. For the rural type systems, it's the other way around. You assume they get no water unless there's enough to hand out. And so we have these resource assessment systems, such as annual accounting, which are used to determine how much water is available to the licence holders. And so it does the seasonal allocation calculations in the model at whatever times the modeller chooses to specify. So I'll now hand over to Karina, and she'll talk about groundwater interaction.
Hi, I'm going to talk to you about groundwater interaction, as Jeff said. Now, in Source, we have a number of groundwater models. There's two main modules. There's the Analytical, groundwater analytical model, and we also have a Numerical model. So groundwater interaction is applied at a link, generally as a flux. The first three models mentioned here, the groundwater flux, groundwater heads, and the analytical solution model, which is unsaturated connection or saturated connection, these will calculate a flux, or they will return a flux between the groundwater and the surface water. The fourth model here, the numerical solution model, will not only return a flux between your groundwater and surface water, it will also return groundwater levels at specified points in the cross-section. Now, the first method, groundwater flux, is the simplest. You'll choose a method depending on the level of complexity you wish to model and how much data you have available, for instance, and what type of data. So the first model here, groundwater flux, you just specify a flux time series. The second one, you specify heads, if you have a head time series, and it will use the relative levels in the link and the groundwater level to calculate the flux. The third one here, I'll talk a bit more about in a minute. And we have unsaturated and saturated connection models. Now here shows the saturated connection model. It's you accumulate the effects of a number of different processes to calculate an overall flux. The processes include groundwater pumping from a single point, irrigation recharge over a specified area, evapotranspiration over the full area, bank storage from rising and falling of the water levels within the stream. You can have gaining or losing water from general low flow, and overbank events, where you can specify a overbank feature and it calculates occasionally when the water level is exceeded how much water will infiltrate through that overbank feature. These are all accumulated together to calculate an overall flux. Now, the unsaturated connection is you use the unsaturated connection model in the case where you know that your groundwater level is always going to be below the level of the stream. Excuse me. and it will always be a losing situation. So water will always be higher in the stream than the groundwater level, so you always lose water, so it'd be a negative flux from the river. This is an example of a screenshot of the saturated connection model. Then, as I said, there's a number of different processes it models. In this particular case, most of those processes are represented. Things like diffuse recharges and point recharges and pumps, both semi-confined and unconfined pumps, can be specified as a time series input from a data source. You'll notice at the top of this screen there's common controls. So these common controls have to do with the soil properties of the area. There's a there's transmissivity and specific yield that are soil properties, and it also defines the floodplain width, and so there's the dimensional properties of the aquifer. This slide here demonstrates or shows what the numerical model represents. It's actually a cross-section, full cross-section of the, it represents a full cross-section, and you can specify a number of elements within each bank. It's fairly easy to use. It will calculate groundwater levels. It will calculate groundwater levels based on the cross-section. There's also an unsaturated zone represented for overbank type events. There's very similar processes that are modelled in the numerical model as are represented in the saturated connection model. Here is an example of a GN1D numerical model screen, which shows the sort of things that are specified here. You'll notice down in the bottom right corner there's an edit cross-section section. So in each of these models you'll need to specify your cross-section, and it'll specify where your left and right bank is, and you'll create a rating curve for that cross-section, which will allow source to calculate what level the water is in your link. I won't go into great detail about this. There's a lot of processes represented. We have much the same sort of process, as I said before, as the analytical model, but in this case we can actually specify. You can see here the observation bores. You can specify locations of observation bores, and it will calculate, it will give you an output of the groundwater level in those observation bores. I'll hand you back to Jeff now for concluding the seminar, or Meryl?
Well, thanks for attending our webinar, everybody. I'd like to just remind you that if you have any questions, you can either use the question functionality to type your question in, and I'll see them on my screen, and I'll get the appropriate hydrologist or developer to answer them. An alternative to that is you may see some functionality to raise your hand. If you have a microphone, I can attempt to unmute you if you would like to ask your question verbally, and we can have a conversation. A lot of the functionality that you've seen today is available through our betas. Our current production release is at 3.71, and some of this functionality that Jeff has demonstrated is 3.816. If you're interested in obtaining a beta, you do so through a support and maintenance agreement. If you have a look at your handouts on the right-hand side of your screen in your control panel, I've attached a support and maintenance brochure and also a general source flyer if you need to explain what source is to anybody else. I'd also like to remind you that this is a precursor to a course that we will be running on the 17th and 18th of November in Brisbane, where you'll have an opportunity to explore these issues in further detail. We have a question, is this webinar available after this session with the recording? Yes, it will be. You'll receive an email within a day or two accessing the recording, and if you'd like to share the recording with someone, we'll also put it on our YouTube channel along with all of our other previous webinars. Are there any other questions? So far we don't have any. We'll be on the line for another few minutes, but thank you very much for joining our webinar.